The universe does not hand out second chances. In the vast silence between stars, worlds are born, transformed, and destroyed by forces that operate on timescales almost too large for the human mind to hold. Our solar system is no exception. Within it lies a story of creation and annihilation, of moons shattered and planets thrown off course, of water delivered across hundreds of millions of kilometers to land on a single pale blue dot. And at the center of it all burns a star that has been the architect of everything we know and everything we will ever become. 4.5 billion years ago, a vast cloud of gas and dust began to collapse under it. Pulled inward, it spun faster, flattening into a disk with a burning young sun at its heart. Within that disk, tiny grains of material collided and clumped, growing from dust into pebbles, from pebbles into boulders, and from boulders into worlds. The planets we know today are the survivors of a chaotic and violent construction process, and the scars of that process into every crater, canyon, and magnetic field that persists to this day. Jupiter was the first giant to emerge from this primordial disk, and its sheer size made it a force that would shape the destinies of every other body in the solar system. As the young Jupiter swept the inner regions of the forming solar system, its immense gravitational pull toward the early asteroid belt, flinging material outward into the depths of space and scattering the building blocks that smaller worlds needed to grow. Mars, forming in Jupiter's shadow, was robbed of the mass it needed. Rather than growing into a world the size of Earth or Venus, it stalled at roughly half the diameter of the planet. That size difference would prove to be catastrophic in ways we could have predicted at the time. Yet Jupiter's wandering was not all destruction. As it migrated inward, Saturn began its own journey and eventually caught up into a gravitational rhythm that reversed Jupiter's course. Together they pulled back, and as they retreated through the asteroid belt a second time, they hurled water-rich material into the inner solar system. The oceans that today cover more than 2/3 of Earth's surface may owe their existence to that ancient gravitational dance between the solar system's two largest worlds. Jupiter and Saturn moving in precisely the way they did, Earth might have been a dry, lifeless rock. The difference between a world that holds onto its water and one that loses it forever comes down to one critical ingredient: a magnetic field. Deep inside the Earth, liquid iron churns in loops, generating a powerful magnetic shield that deflects the constant stream of particles pouring from the sun. Without that shield, the solar wind would strip away the lighter components of the atmosphere over millions of years, erasing the conditions that make liquid water possible at the surface. Earth has maintained this protection continuously for billions of years, and the result is an unbroken chain of oceanic history and biological evolution that has never been interrupted. Mars once enjoyed the same protection. In its earliest history, the red planet possessed a liquid metallic core, generating a magnetic field strong enough to atmosphere and liquid water across its surface. Ancient rocks on Mars still carry the magnetic signature of that era, a frozen record of a world that was once far more Earth-like than the barren wasteland we observe today. But because Mars is smaller, its interior cooled more quickly. Around 4 billion years ago, the dynamo that sustained its magnetic field switched off. The invisible shield that had protected the Martian atmosphere collapsed, and over hundreds of millions of years, the solar wind quietly dismantled everything it had. The water locked in the polar ice caps today, the thin carbon dioxide atmosphere pressing down at less than 1% of Earth's sea level pressure, are all that remain of a world that might once have harbored life. The hydrothermal systems on early Mars were particularly compelling. In a deep ancient basin formed billions of years ago, what may have been a sea larger than many of Earth's great bodies of water combined. Heat rising from the planet's interior would have driven underwater volcanic vents, creating the same scientists believe sparked life on the early Earth. The timing was remarkable. To have taken hold on Earth roughly 3.5 to 4 billion years ago, and geological evidence suggests similar conditions existed on Mars at precisely the same moment. Whether that parallel story ended with actual living organisms or simply with favorable chemistry is a question that spacecraft continue to investigate. The gas giants of the outer system operate by entirely different rules. Saturn, the second largest planet, sits so far from the sun that sunlight alone cannot drive its weather. Instead, energy rises from deep within the planet itself, generated by pressures so extreme that ordinary physics struggles to describe them. Below the cloud tops, the weight of Saturn's atmosphere increases by factors that quickly overwhelm anything found on Earth. At great depths, methane breaks down and carbon precipitates as graphite before the surrounding pressure compresses it into far more precious. The diamonds that likely form within Saturn dissolve long before they reach its deepest interior. But as they fall and melt, they release heat, and it is heat that drives the extraordinary storms churning at the planet's surface. Neptune presents an even stranger puzzle. Despite being far more distant from the sun than Uranus and receiving proportionally less solar energy, Neptune is actually warmer and dramatically more active. Its atmosphere seethes with the fastest winds measured anywhere in the solar system. Storms spinning through temperatures that plunge to nearly 200 degrees below zero. The contrast with Uranus, which is remarkably featureless and cold despite sitting closer to the sun, remains one of the genuinely unresolved mysteries of planetary science. Ice giants emerged from similar material in similar regions of the early solar system, yet they evolved in radically different directions. Understanding why they diverged so illuminates something fundamental about how planetary interiors evolve. Uranus itself carries the unmistakable marks of a catastrophic ancient collision. Every other planet orbits the sun and rotates on an axis that is more or less perpendicular to the plane of their orbits. Uranus rotates almost entirely on its side, with its roughly toward the sun. The most compelling explanation is that a body roughly the size of Earth struck Uranus during a period of intense early bombardment, permanently knocking it off axis, the internal heat that might otherwise have kept its atmosphere dynamic. Without that heat, the atmosphere stagnated into a featureless cold expanse. The ring system, orbiting nearly vertically in alignment with the planet's tilted equator, stands as a permanent record of the violence that once rewrote this distant world's geometry. Mercury, the innermost planet, carries its own peculiar history written in chemistry rather than collision scars. Its metallic core is disproportionately enormous compared to the thin, rocky mantle that surrounds it. That puzzled planetary scientists for decades before the first dedicated orbiter arrived to take a close look. When that spacecraft analyzed the surface in detail, it detected volatile chemical elements in concentrations that should not survive so close to the heat of the sun. Those elements evaporate at relatively modest temperatures, and the radiation environment near the sun would have driven them off long before Mercury solidified if the planet had always occupied its current position in the solar system. The most persuasive explanation is that Mercury formed significantly further from the sun and was displaced inward by gravitational encounters with other planetary embryos during the solar system's turbulent formative period. A glancing collision somewhere along that journey likely stripped away much of its original crust and mantle, leaving behind the dense iron-dominated we observe today. The sun has presided over all of this history as a middle-aged star stable enough to allow complex life to emerge and flourish on at least one of its 8 planets. But that stability is not. The sun has grown slowly hotter and more luminous over billions of years. The trend will continue. Roughly a billion years from now, the added heat will push Earth's climate toward a threshold that complex life cannot survive. Billions of years after that, when the sun exhausts its hydrogen fuel, it will swell into a red giant, swallowing planets and transforming the inner solar system beyond recognition. The conditions that made Earth exceptional, the liquid oceans, the stable atmosphere, the enduring magnetic field, are not permanent gifts. They are a fortunate alignment of size, chemistry, and timing. The planets of our solar system are not static monuments. They are dynamic, evolving worlds whose stories are still being written. And every mission we send into that darkness returns with evidence that the universe is stranger and more extraordinary than we had dared to imagine.